So in this video tutorial we will discuss biaxial state of stresses. The general biaxial state of stress is shown here. Here it is the stresses are acting in two directions, x direction and y direction. And one specific case for this is shown here in this figure. So in this figure, load F is applied and we are interested in finding out the state of stress at any point on this member AB. So if we consider point E, then we find that this load F induces bending and twisting at this point E. And bending is because of the bending moment that is being produced by this transverse load F, and the bending moment at this point is F into L. 0 here, and then it is increasing linearly, and maximum value of bending moment is here, that is m into L, F into L. And the twisting moment is acting F into E, which is constant from this point to this point. So there are two effects of the load. One is bending moment and another is twisting. There is another effect of load, that is transverse shear here, but we will neglect transverse shear because its transverse shear induces very less stress as compared to the bending stresses and twisting torsional stresses. So generally we neglect that. So here also we will not be considering the effect of this transverse shear that will be there at this point E. So in this particular case, the bending moment diagram and twisting moment diagram is shown here over the length AB. This is specific case of biaxial state of stress, and in this case the stresses are acting along x-axis, that is due to bending, and shear stresses, that is tau xy. But this particular case is general state of stress. We can have the normal stress is in two direction with shear stress, and for this particular case xy is the coordinate axis system, and if this is the state of stress, then there, just see, if we consider this plane and we move this plane from here to here, then we find this stress sigma x, normal stress sigma x varies, and then finally here on this plane this sigma this normal stress changes to sigma y. So it means there must be the variation in the normal stress between within the element, and that particular normal stress will vary from when we move plane from here to here. So the effect of this state of stress will be different within this element. So to consider this, let us consider a element. Let us take an inclined plane AC. This inclined plane AC on this axis system XY is making an angle theta. This is basically can be considered that this XY axis is rotated through angle theta, so that this Y axis become inclined to this original y-axis inclined to this by some angle theta. So either we consider that this is some inclined plane at some angle theta, or we can also consider the same thing, that is the transformation of this xy axis by some angle theta in anti-clockwise direction. So sorry. So we will be obtaining what are the stresses acting on this plane, normal stress as well as the shear stress. So let us try to find out the transformation of the stresses, or the stresses, normal and shear stresses acting on this plane. So for that we will consider the static equilibrium of this small element, and for static equilibrium certainly we have to represent the forces, not the stresses. So this is how the forces are represented on this. So sigma theta is the normal stress on the plane AC, and tau theta is the shear stress on this plane. So both whatever state of stress here shown here on the element and the state of stress on the inclined plane all are positive, because this particular sigma theta is outward normal, which is positive, and this outward normal, and this is also positive, this is along y dash. So both are positive, so this state of stress, the assumed state of stress, is also positive, multiplied by the area, assuming that T is the thickness of this element. So AC multiplied by this thickness will give us area. So this is also force, this is also force, normal force and force perpendicular to this normal direction x dash. So we can have the static equilibrium equations like this. And for static equilibrium, now we have two uh, basically a method of analyzing this. Either we resolve everything along this x dash and y dash, or n or t that represents normal and the uh, tangential component. Otherwise we can say it is x and y axis is rotated along x dash and y dash. So either we resolve everything along this n and t direction, or we can resolve as usual x and y direction. So let us resolve this in along n and t direction, and then we write down the equations. So when we resolve these forces, because two forces are acting here, so we will be having four components here. Two forces are acting here, we will be having four components. And to just see, to mark everything, all four components, resolved component correctly or cleanly, we have extended these lines, and then we will be marking on this, that is along normal direction. So this fxab is the force along x axis that is acting there due to sigma x, presence of sigma x. Then fyab, that is due to tau xy. Then fxbc, it is because of tau xy on face bc. And then fybc, that is along because of the sigma y. So now let us try to resolve these components. So this, when we resolve these components along n and t direction, or x dash or y dash direction, so these are the resolved component. This angle is theta, because this theta is between this and this line, and this line is perpendicular to this inclined plane AC, and this line or line of fxab is perpendicular to the face AB. So that is why these the angle between two lines will be, as we know, the angle between two lines is the angle between two perpendicular lines. So that is why the angle theta is same. So now we can resolve this into two x and y component, that is shown here. Next we can resolve the other component. Again the same concept we can use to mark the angle theta, that both lines are parallel, which is, so AB F YAB is parallel to this AB, and this particular line is parallel to this line. So angle between these two lines will be theta. So now this is cos theta, this is sin theta, and similarly we can mark the other components. So now we have 8 force components, and now we can write down the equations of equilibrium as summation Fn0, summation Fn0 will give us this, finally this equation. We can further reach to this final equation after simplification, as done here. Similarly, we can make use of another equilibrium equation, that is summation Ft is 0, and then we get this final equation, tau theta is equal to 0. So let us once again reiterate this particular concept, that we have uh, rotated this xy axis by angle theta, so that we get x dash and y dash. X dash represented by n normal direction, and y dash is represented by this t direction. Now just see if the other thing that I would like to explain here, we have not considered the equilibrium our resolution of forces along x and y, because in case when we resolve forces along x and y direction, then sigma theta and tau theta will be appearing in both these equations. And as we are interested in finding out sigma theta and tau theta, so we get two equations both in sigma theta and tau theta, and then we have to simplify those two equations obtained by this f1 is equal to 0 and ft is equal to 0 to get the value of sigma theta and tau theta. But here in this case, when we resolve everything along n and t, or x dash and y dash, we get one particular solution from one equation directly. We need not to further simplify. That is the advantage. That is why we did not resolve these in along x and y. Now just see if when we see that here the normal stress is sigma x, and on this normal stress is sigma y, when we revolve this and then reach to this, the stress is changes, and in between this some this is one thing. And similarly it is tau theta, it is also moving from here to here, and finally also it's same, so it means must be varying somewhere. Another thing, that sigma theta is also having one constant component, whereas these two components are varying sinusoidally, and here both the components are varying sinusoidally. So here it is less likely to get sigma theta 0 within the element. The only one situation in which we can have this may be 0, that is when this constant term is 0, and that is the case when sigma x is equal to sigma minus sigma y, and only then this particular component will be 0, and then we have only this component. So but here this is varying with respect to sine and cos curve, so that is why this may be 0 somewhere. So let us try to find out where this sigma tau theta is 0, and let this at that particular point theta becomes theta p. So now we can write down, when this substitute this is equal to 0, we get tan 2 theta p is equal to 2 tau x divided by sigma x minus sigma y, and this particular value, this particular expression gives us two values of 2 theta p and 2 theta p, that is a gap of pi is there, so theta p is changing by pi by 2, so we'll be getting two values of theta p, and both those two values are are at 90-degree of angle. So hence there exist two planes at pi by 2 apart where the shear stress is 0. Such planes are called principal planes, and the normal stress on principal planes are called principal stresses and represented by sigma 1 and sigma 2, that we all very much aware of. So now we can write down the how to find out these principal stresses, that is our aim. So we have discussed and obtained three expressions till now. Sigma theta, that is the normal stress on the inclined plane or the transformed axis. Tau theta, that is the shear stress on the inclined plane or the transformed axis, and tan 2 theta p, that is the inclination of principal plane. So now let us use this tan to triangular form of tan to theta p, that is the perpendicular upon hypotenuse, to get this particular triangle, and then we can write down sin 2 theta p and cos 2 theta p. We are using p1 to mark the first principal plane, and the second principal plane will be 90-degree apart. So this is how we can get these values. Sigma 1, substitute back into this equation. When we substitute this, theta is equal to theta p 1, so we get value of sigma 1. So when theta is equal to theta p1, sigma theta will be equal to sigma 1. So we can substitute these two values to get value of sigma 1 and sigma 2 respectively. So in general we write this type of expression, and we can also mark the state of stress on the principal plane as shown. This is our original element, and the state of stress on the original element is like this. Let us mark principal plane here. Whatever equation, whatever angle we have obtained, we have marked the principal plane. Now we can mark the second principal plane. This is second principal plane, which is 90 degree plus this. So now we can draw one small element on the principal plane. So now we can mark these stresses, that is sigma 1 and sigma 2. Sigma 1 is the normal stress on principal plane, first principal plane, and sigma 2 is the normal stress on second principal plane as shown here. So we can also find the plane of maximum shear stress. So maximum shear stress means there may be some value where shear stresses are maximum. If there exists, there may not, even it may not exist. So let us try to find out what is the value of maximum principal stress and where it exists. So we have to differentiate this tau theta, so to get the maximum value and then to equate it to 0. So this is how we can do it. Differentiated, equated to 0, we get tan 2 theta s as this expression. If we see two expressions, one is tan 2 theta p and another is tan 2 theta s, we find that these two angles are perpendicular to each other because the product of these two angles, it is slope, rather the product of these two slopes or angle, tan angle, is -1. So when the slope is -1, the product of the slope is -1, it means the two planes are perpendicular to each other. So this is what basically we obtain. It means that 2 theta p and 2 theta s, they are perpendicular to each other. It means theta p and theta s will be at 45 degrees. So once we obtain principal plane, we can get value, we can mark the principal plane of maximum shear stress by at a distance of 45 degree. So state of stress, let us mark the state of stress at a point on plane of maximum shear stress. So the value of maximum shear stress, again we can make use of this 2 theta p and take this triangle, find out the tan 2 theta s and tan 2 theta, cos 2 theta s and sin 2 theta s, substitute the values here to get this tau maximum. So this is the value that we get of tau maximum. So this is what we obtain. Now let us try to mark the state of stress of on the plane of maximum shear stress. So this is the diagram that we have drawn. We have marked the original element. We have marked two planes, principal planes, and now we can mark the plane of maximum shear stress because this is principal plane, and at 45 degree we can mark a plane of maximum shear stress. So this is pi by 2, that is theta s1, and it is pi by 2 plus theta as a p1. So theta p1 plus pi by 2 is theta s1. Similarly, we can mark another plane of maximum shear stress which is 90 degree from this, or it is pi by 2 from the second principal plane. So this is how we can mark here. Now we can draw one element here to represent the plane of to represent the state of stress on this plane of maximum shear stress. Now we can mark the stresses like this. So this is how we can mark. We can finally further prove that this sigma s1 and sigma s2, they are equal and opposite at the plane of maximum shear stress, though we have shown in the same direction, but they are equal and opposite. That we can substitute when we substitute this sin 2 theta s and cos 2 theta s in sigma theta equation. So this is how we can represent the state of stress on at a point on the plane of maximum shear stress. So this is how the angles and other things are measured in on this when we solve a numerical problem. The Here in this case, this can be considered as the transformation of xy axis to x dash and y dash, and theta will be considered as positive. And this is the revolved, this is the transformed, uh, you can say, element. So this would be x dash, y dash, and all that. We have the different values, and this particular, if we revolve this, rotate this in this, so that this y becomes like this, so it means we have rotated the axis in negative direction. So these things is to be considered for considering the values of this, and everything is positive here, the positive state of stress, whether in terms of x and y or in terms of x dash and y dash. And let me once again remind what is the positive state of stress. A stress is considered to be positive if the direction and the plane in which the stress is acting both are positive or both are negative. So it means here this is the positive direction of plane x-axis, this is the positive direction of stress y. So both are positive. The sigma x is positive and tau xy is positive. Here in this case, the direction of plane is negative and the direction of stress is negative. So both are negative. So that is why sigma x is positive. So here the plane is negative and the direction is negative for shear stress. So that is why this shear stress is also positive. So this is positive shear stress. If we consider here the revolved or the rotated or transformed axis y dash, so this is x dash negative direction and this is y dash negative direction. So that is why this state of stress is positive. So if we calculate or obtain negative values, it means the directions have to be shown accordingly. So this is all about biaxial state of stress. We'll consider more circle in next lecture. Thank you very much. For more stuff, visit www.classconnect.in and register there. Thank you.